Okay, let's prove exercise 1.1.4. We want to prove that the given kind of function is a metric on R2. Then the meaning of to prove that a given function is a metric on certain set is to showing that four properties of this metric definition. Okay? So at this moment, this is definition for metric. So the set is just arbitrary set X. But if we use two real numbers, then it should be R cross R. Right? But no matter what the set you start with, the function value for the metric should be real number. Eventually turns out non-negative real numbers, which means the metric is actually the distance. You can imagine that way, right? The measurements between two elements in any set. So let's just try to prove that given the function, right, on R2 is metric. Okay, so let me go down to make a space. So from the beginning, we have to start with defining the set, the function d itself, right? So let me arrange a little bit here. Okay, so let me rewrite. So this is proof. Let me rewrite that the d, right? Right now, dxy is 0 if x equals y, or is 1, otherwise means if they are not equal. Okay? On R2, and R2 means we have ordered pairs, right, from R2 space. So key point here is x comma y and y comma x are totally different elements in R2. Right? So we don't know whether the commutator is working or not, even for writing down for the metric. And if we just only R2, then xy is here, then y comma x should be around here, right? So they are totally different points. So we cannot claiming if something happens and true for dxy, then it should be also true for dyx. We don't know that. So that's the one key point in the proof. So let's just try to prove. The first thing is no matter what. So let me write down that properties here. dxy should be greater than or equal to 0 for all x and y in R at this moment, right? Not x. Careful. So that's the statement, and we need to prove that. And if you just choose any elements, x, y, from the real number set, then we have only two choices. Either x must be equal to y, or they are not equal to each other. Right? Then, if they are equal, then dxy must be 0, or dxy must be 1. We don't have any other choice. That they are the only cases that we might have. Okay, so altogether we can claim that dxy for any xy should be greater than or equal to 0, because it's either 0 or 1. So, we prove the first property. The given D satisfying the first property to become a metric. Okay. Second statement or the property for being a metric is dxy equals 0 if and only if x equals y. Now, in mathematics, any statement has if and only if means actually you are dealing with two different statements, okay? Not only one. So you have to prove two things. First, let's say, let x equals y. So we want to prove, if you want to point out that direction, right? Starting from the right hand side and go to that left hand side. Okay? So let x equals y. Then what happens by the definition? of dxy in this question, we can claim that the dxy must be equal 0, right? Okay, we got the result. Okay, so that the first part is okay, but the second one, we have to prove this direction too. So we have to start with dxy is 0, and we have to show that xy must be same real numbers. Now the problem is, in the given definition of a d, there is no such thing, right? We always kind of start with comparing these two xy's, right? If they are same, then dxy must be 0. If they are different, then dxy must be 1. That's all we have from the definition. So we cannot guessing or claiming that, oh, if dxy is 0, then yeah, xy must be equal. We cannot say that. There is no guarantee about it, right? But to prove it, because the nature of the given the d is always starting from whether x equals y or x is not equal to y. Okay? So do you remember? So this is the one in logic. If you want to prove p implies q, the contrapositive, like not q implies not p, if you show that is true, then this is also true, because the truth value for original conditional statement and its contrapositive should be same. Both of them at the same time true or false, right? Not sharing true and false altogether. So just imagine that is P, right? And the result is Q temporarily. And now we want to prove P implies Q, which we don't have any tools. So let's try to prove the contrapositive of it. Then if we show that is true, then we can claim the original, that statement is also true, okay, by that logical statement. Okay. So what is not Q? Okay, so let x is not equal to y. Then same reason, by the definition of dxy, we can claim that dxy equals 1. So we just show what? It's not 0, right? So which means dxy is not 0, which is negation of that p part, right? So we start from not negation of q, not q, and we arrive not p. Hence, we can claim that dxy equals 0 implies x equals y. Now we can go either direction, right? If x equals y, then dxy is 0. If dxy is 0, then x equals y. There's no other way. Because of this, after we prove this part, okay? So we prove the second properties to being a metric by that. And the third one, we want to show the commutative for notation for d, like a dxy, dyx should be same no matter what. Okay? So the statement itself is dxy equals dyx for no matter what xy is, right? Okay, that's the statement. Okay, so prove it. So first of all, we have kind of two choices, right? Okay, so let's say dxy could be 0 or 1. We only have two choices. So let's start from there. Okay? Let me cut down let and if, then, right? Let me just simplify it this way. So if dxy equals 0, which means x must be y because of the previous condition, right? You cannot just say it because definition doesn't say anything about these properties. Then y equals x in real numbers, right? we cannot say this one guarantees dyx is also 0. We don't know. We need to show it, right? So you cannot just claim that way. So we just move this kind of statement into real world, right? Real number system. Then in real number system, x equals y, you can claim y equals x. We can flip this order, right? But because of the definition of D, if y equals x, then the yx equals 0. Okay? So look at here in D, in math, the order is very important. X equals y or x is not equal to y. That's the order. You can put x comma y here, right? You cannot say dyx equals 0 if x equals y. No, unless the definition is given that way. So the order is very important in math. So please keep that in your mind. And that's why we spend time just simply showing these two values are same, right? If is 0. So second case is if x, y is not 0, then we only have 1, right? That's the only choice. Then by the definition, x is not equal to y, which means y is not equal to x. Then by the definition of D, we can claim dyx should be 1. So from both dxy, dyx is the same, no matter what the value is, right? So we can claim finally, okay, dxy must be dyx for no matter what x, y's are, whether they are equal or not. Okay, the last one. That's the longest one, craziest one. So most likely that triangle inequality is the always big portion in the definition of metric or whenever you want to show it. You want to prove that inequality among these three values, right? No condition for that values. It can be any real numbers, but no matter what, the sum of these two kind of D's is greater than or equal to just one of them. Okay? So you can separate this one into several cases. What happens? Let x, y, z's are all same, right? Then dxy, right? So some of it, you might say, oh, 0 plus 0 is greater than 0. Yes, but in proof, where did you get it, right? So it's not that much kind. Okay? So please don't do that. It's better to say that like a D. So then dxy plus dyz equals 0 plus 0, which is 0, and dxz is 0 because they are same number. Hence dxy plus dyz is greater than or equal to dxz. Okay? It's going to repeat, so if you don't like it, you can just claim that one here, and you can write down this one at the end after finish all these different cases. Second one, okay, the first two are same, but not the third one, right? Then you know what you should do, right? So that dxy plus dyz is 0 plus 1, and xz's are not same, so it should be 1, then still you can keep that one, right? So you just to show those cases. And be careful, it depends on how you separate them, right? Okay. So in this case, the third one is if you really want to separate nicely, and you have to show that much. And finally, they are all kind of different. Okay? And this is not good because this statement says x is not equal to z and z is not equal to y, but it doesn't say anything about whether x, y is equal or not, right? So it's better to say all x, y, z's are different or distinctive real numbers or something like that, right? Instead of that notation. But anyway, so you can show all these properties. And that's the end of proof, okay? Hopefully this is helpful for the future proof or any other statement in mathematics.